Hi everyone, my name is Lars Kroll, and in this lecture I will describe a few real-world distributed systems and how they relate to the concepts you learned in this course. This lecture is divided into three parts. In the first part I will describe three systems that are either implementations or variants on the sequence Paxos algorithm. In the second part, I will describe two systems that use Raft as their underlying mechanism. And finally, in the third part, I will describe two closely related systems that implement the shared memory abstraction with weaker consistency guarantees. The description of these systems will mainly be based on papers or documentation that is freely available, and I will note below every page what paper or papers to read if you want to know more. So let's take a look at Paxos implementations and variants. The first system we're going to look at is called Chubby, and it was developed at Google in 2006. And it basically provides a distributed log service. That is, it is a way to, throughout a cluster, take temporarily ownership of a resource. And in Chubby, resources are addressed like in a file system by paths that identify nodes, and these nodes are what logs can be taken on. And in addition to that, nodes also have associated metadata, for example access control lists, that allow them to be used in conjunction with the permission system. And to a large degree, Chubby has replaced Google's internal usage of DNS as a name server. The Chubby system runs on an implementation of sequence Paxos with leader leases as we have described them in the course, but the implementation is based on RPCs instead of message passing. The second system I want to talk about is also developed at Google. It is called Spanner, and it is a globally distributed database. Like a traditional SQL database, Spanner supports schematized data. It also supports multiple versions of the same data item in parallel, and it supports false transactions. And like Chubby, Spanner runs on sequence Paxos with leader leases. But the special thing about Spanner is that it uses a particular implementation of what we've described in the course as interval clocks based on what Google calls a true time API, which gives them very small intervals due to the use of GPS clocks in each data center. And this allows Google to get very high throughput transactions in Spanner. The final entry in the Paxos group is Apache Zookeeper, a system originally developed at Yahoo, and it is currently used by a very large number of open source projects. For example, Hadoop, Spark, Flink, Kafka, and a number of others. Technically, Zookeeper is a distributed key value store, but it is usually used as a log or synchronization service and often for storing system configuration values such as snapshot IDs or group membership and so on. Zookeeper runs on a protocol called ZAB, Zookeeper Atomic Broadcast, which is effectively a variant of sequence Paxos where slightly different design decisions were made. One of them being the use of passive replication, meaning that the master node applies an operation and then merely broadcasts the result instead of broadcasting the operation. And Zookeeper is also not built with reconfiguration of their groups in mind, only fail recovery. Next, we're going to talk about two systems using Raft instead of Paxos as their underlying implementation. The first system is called CockroachDB, developed by a startup called Cockroach Labs that was founded by former Google engineers who worked on Spanner. And CockroachDB is a distributed key value store that offers ACID transactions and based on that offers the developer a full SQL API. It is backed locally on each machine by a key value store called RocksDB, which is an embedded database. And in general, the design of CockroachDB is fairly similar to Spanner, but the developers made a purposeful decision not to use TrueTime to avoid the dependency on having GPS clocks in every data center. And all operations of CockroachDB run on Raft, and the whole system is written in Go. Another key value store called etcd is developed by the people at CoreOS, who are also responsible for Kubernetes. And like Zookeeper, etcd is typically used for storing configuration values or distributed synchronization. And like CockroachDB, etcd runs on Raft in Go for all operations. Finally, I will talk about shared memory systems with weaker consistency guarantees. And the first one here is Dynamo, which was developed at Amazon and is an eventually consistent key value store, meaning that instead of providing linearizability for all its values, Dynamo only offers the guarantee that eventually, if no further writes occur, there will be a single value for each key. And the reason they made this decision is to focus Dynamo on availability over consistency. One of the mechanisms allowed by this choice is that in Dynamo, for every operation, you can pick the size of the quorum you want the operation to have, and in this way you can trade off throughput and latency versus the probability of creating multiple conflicting values that need to be reconciled later. Dynamo uses vector clocks to track causal dependencies between different values on the same key, which allows them to automatically reconcile causally related values and avoid the manual reconciliation that is required for causally unrelated values. Another interesting feature of Dynamo is that in case of diverging replicas, it uses a background synchronization mechanism to reconcile the different values in the diverging replicas. And the mechanism it uses is based on a concept called Merkle trees, where effectively a hash tree of a partition is being built up and then exchanged level by level to find out where exactly the replicas diverge, to avoid having to copy all the data in a partition between diverging replicas. The last system we're going to talk about today is Cassandra, which was developed at Facebook and is basically a re-implementation of Dynamo, but introduced a few new ideas. For example, in Cassandra, there is a notion of tables, which they call schemas, that force values in a particular range to have the same layout. And based on that, Cassandra supports column families, an idea that comes from Google's Bigtable. Another difference to Dynamo is that Cassandra does not rely on vector clocks for automatic reconciliation, but instead simply uses loosely synchronized clocks with a last write wins mechanism to automatically reconcile all values